Hey, Algebra 2 honor students, this is functions day 12. We're nearing the end of the unit, and we're going to be continuing our discussion on piecewise functions. So building off of yesterday's lesson, as a quick reminder, I've defined a few things for you at the top here. A piecewise function is made up of different pieces of functions that are graphed over restricted domains. And what we've seen a lot is that typically they have more than one function family that's involved in the sketch. So we saw that a lot in the homework and then in yesterday's notes. Today we're going to add on some new vocabulary words that are typically associated with functions of this form, the first one being continuous. So a function is said to be continuous over its domain if you can draw the entire graph without picking up your pencil. Okay, so that's kind of an informal definition of continuity, but I think it's the easiest for us to be able to determine where a graph is continuous, or more commonly, we'll actually be talking about where a graph is discontinuous. So when you pick up your pencil, the graph is said to be discontinuous at those specific values of x. Then we're also going to look at graphs today and describe where the graph is increasing, decreasing, or constant. And these are intervals on the x-axis. So a lot of what we talked about has to deal with x values. And what we're going to analyze is if the y values are going up, going down, or remaining the same when we move from left to right. And that left to right part is actually pretty important. Okay, and I'll explain why in a second here as we look at the graph that's given to you in the notes. So this is kind of looking like a pretty classic piecewise function. We've got a linear part. This kind of looks absolute value-ish. I'm not sure. I guess it could be two lines that make that up, and then a constant function at the end here. So the first part says, where is f of x continuous? So if I start on the left side of the graph, I mean, certainly it's going to kind of head down forever and ever. So it's continuous from negative infinity all the way up until I get to this hole in the graph at x equals -3. So we're going to start by saying negative infinity up to and including, well, we can't include -3 actually because of the open circle. But then once I make a big jump up here to the next part, this V-shaped part of the graph, we can create a union and say, hey, this whole part of the graph is continuous. I can draw it without picking up my pen. So that includes x values from -3 over here to +4, right? So I'm going to say, because this is closed, we'll use a bracket at -3, and then up to +4. But as I approach 4 on this part of the graph, we can see that we're approaching an open circle. So we'll make sure that that's parentheses there. Once I make the final jump down to this flat part of the graph here, we can say that the graph is continuous from this point and then forever to the right. So we'll say from 4 to infinity, but for that last piece of the graph, we can include 4 because of the closed circle. So when we talk about where the graph is continuous, we're talking about the intervals over which we can draw the graph without lifting our pen or pencil. And we only have to lift it twice, once at x equals -3 and once at x equals +4. So for that reason, actually off to the side, I want you to write down that this is therefore discontinuous at x equals -3. And at x equals +4, which is a much easier statement to write than listing all the intervals over which the function is continuous. But hopefully, either way around it, we should be able to list this information depending on how the question's asked. As far as the next pieces for where is the graph increasing, decreasing, and or constant, what I'm going to recommend is always start on the left side of your graph, like it suggests up here, we're moving left to right. And this is going to sound a little weird, but I like to kind of put like a little person, a little stick figure on the graph on the way left side. And think about, what does this person have to do to walk from the left side of the graph to the right side of the graph? And the very first thing that person has to do is they have to walk uphill. They're heading this way from left to right. So the very first part is we're increasing from negative infinity up to -3. So we can write that down for increasing. Students very commonly look at this and say, no, Mr. All, the arrow's pointing down, it's decreasing. And I can understand why you would say that, but in this case, you'd be moving right to left when you describe that. So make sure that even if the arrow is, quote unquote, pointing down, it doesn't mean that we're decreasing. You want to analyze the graph from left to right. And hopefully you can see we're going uphill there. All right, then at -3, we know we have to make that big jump. So now I'm standing up here on top of this little mountain. And the next thing I'm going to do is from left to right. Now I have to go downhill, which to me indicates that we're decreasing. So we're going to be decreasing from -3 until I get to the bottom here at x equals 0. Notice how when I'm about to write decreasing, I'm only using parentheses there. And that's kind of important because when I get to this point at the bottom, how do I know if I'm decreasing or if I'm increasing? And the answer is you're not really doing either. So when we do this part with increasing, decreasing, and constant, we're only ever going to use parentheses to describe these intervals. You'll never use brackets like I used up here in continuous. And we know we can use brackets when we describe domain and range, so we'll get to that part in a second. All right, and then what happens once I get to the bottom of the hill? Well, now the person's down here, and they're going to have to, walk back uphill from 0 to 4. So since we're increasing from 0 to 4, you can go ahead and create a little union here, because we already had one part of the graph that was increasing, and say, okay, well, it also increases from 0 to 4. And then we make the final jump, right? So we're standing up here, and we make the jump down to this part of the graph. And since as we increase, the y values remain constant, that really makes sense to me, that we're going to call this a constant graph from 4 to infinity. Again, even though that's a closed circle at x equals 4, do not include a bracket here. That starting point, we can't tell what we're really doing at the start of that interval. All right, so if you have any questions about this, let me know, but really try and focus on, when talking about these three, only using parentheses. Let's talk about the domain and range of this graph. So if I look at the domain, let's see, domain are the x values, right? So if I scan the graph from left to right, I want to see what's included. And where students get a little tripped up with this concept is, remember we were discontinuous at x equals -3, and we were discontinuous at x equals 4. Well, the question I'm going to ask now is, are these x values included in the domain? Is there a closed circle at x equals -3? Yes. Is there a closed circle at x equals 4? Yes. So when I scan all the x values from left to right, I have an x value at every single location. Even though we have these jumps in the graph, there's still an x value defined in these locations where the graph is discontinuous. So this is a little bit weird, but the domain is all reals. -infinity to infinity. Takes a little while to get used to. Is the same true for the range? I'm not really sure. Let's take a look from bottom to top. I mean, this arrow is going down forever, so I know it's at least -infinity, but it appears according to the graph we're going to have to stop at -1, where that open circle is. So we've got -infinity to -1. Okay. And then from there, we're going to go ahead and say, all right, well, we do have a y value at 0, and the y values go up as high as this highest y value, which is at 5, I believe, if I count 1, 2, 3, 4, 5. But since it's an open circle up there, we're going to say that 0 is included, but that 5 is not. Okay, so your final range should be -infinity to -1, union 0 to 5. Okay. Piecewise, there's definitely a lot to consider when we're talking about each of these items individually, but we're going to get some more practice with this on the back. But we're going to graph the functions first. So let's take a look at, as a quick recap, how do we graph this function right here? F of x equals -x plus 1, radical x and absolute value x minus 5 over these intervals. If you're somebody who has taken my suggestion and said, hey, let's make some tables, I think that's a really good idea to get started. So for x values that are less than 0, let's backtrack maybe to like -3, and we'll kind of increase until we get to x equals 0. So negating -3 is +3, plus 1 is 4. And what we'll find, because of the slope of this line is being -1, that the y values will decrease by 1 each time until we get to the point 0, 1. Okay, make sure you indicate, is this last point of the interval open or closed? Well, according to x being less than 0, this should be an open circle. We'll see if the next part fills that in or not. Okay, in the middle, we've got this radical x function from 0 to 4. I'd probably make a quick table that includes each of those values. So when I plug in 0 for x, the square root of 0 is 0, square root of 1 is 1, square root of 2 is I mean, the decimal value is about 1.4, but I don't think we have to worry about that. Same idea, square root of 3 is 1.7-ish. It's not a rational value, so I'm going to skip that for now. But the square root of 4 is 2. Okay. I would box in both of those endpoints and discuss, are they going to be open or closed? According to the inequalities, they are both closed circles. And finally, last one, absolute value x minus 5. Remember, for absolute value, we know it looks like a V shape, so thinking about where that V occurs, where the vertex is kind of important here. When I plug in 4, 4 minus 5 is going to be -1, but the absolute value of -1 is +1. At 5, we're going to get a y value of 0. And then when you plug in 6, you'll get 1, and 7, you'll get 2. And the first point of this interval has to be open, according to the inequality. Okay, the last point from the radical wouldn't fill in that open circle. So using this information, if we go ahead and transfer it over to the graph here, we've got -3 and then up 4. Okay, go ahead and plot these points. Again, it's kind of nice when you have a slope of 1, so you can easily find some other points. Now, as you go to the left here, make sure you extend that graph to the left forever, because we only backtrack to the point -3, 4. We could have gone much further, though, right? So indicate the pattern there. Then we're going to graph the function radical x next. So we've got 0, 0, 1, 1. And the next point that I found that had a nice output was 4, 2. Okay, so that's what the radical part looks like. And then finally, the absolute value graph, we're going to have 4, 1, which is open. Comes down and hits the vertex at 5, 0. And then turns around. And it's going to head back up. So that is what each of the components look like for this specific graph. So I'm going to ask you a few things, even though it doesn't prompt you for any of this here. Let's talk about, where is this graph discontinuous, if anywhere? Piecewise functions don't have to be discontinuous, but really, if there's any issues, it's going to be where these graphs get split up, right? Those intervals along those restricted domains. So are we discontinuous at x equals 0? Did we have to make that jump in the graph? Yeah, we do. And same thing at x equals 4. So there are two values for which this function is discontinuous. If I, on the other hand, said, well, where is the graph continuous? That's a whole set of intervals that represent this graph. So where is this graph continuous? It would be from -infinity up till 0. Remember, we're looking at x values. And then it's continuous from 0 to 4 with brackets. And then finally from 4 to infinity. Once I make that final jump, we'd be continuous there as well. Last thing we might want to include quick, just while we're talking about, is maybe like increasing, decreasing, constant, things like that, like we referenced on the front. So let's see, where is this graph increasing? Well, first part of the graph, I'm decreasing. I'm heading downhill from left to right. Then I'm increasing from 0 to 4 along the radical function. And we're also increasing over here from 5 to infinity, right? Once I get to the bottom of the absolute value, which is at x equals 5. From there to infinity, we're increasing. Let's talk about decreasing. Like I said, we were decreasing in the beginning of the graph from -infinity to 0. And then we're also decreasing over this tiny interval here once I make the jump down to the absolute value between 4 and 5. If I asked you, where is this graph constant? The answer is nowhere. Okay, there's nowhere where we have consistent and constant y values as x increases. All right, so if you have any questions about how we're determining this information, definitely let me know in class tomorrow. But hopefully you're getting a pretty good concept as to what discontinuous versus intervals of where the graph is continuous look like. And then we've got some information about increasing, decreasing, and constant. All right, so we're up to that point in the notes where, of course, I'm going to have you at least try something. Try number 2. Go ahead and make that sketch for me. We'll go over it tomorrow. Okay, make sure you look at this as one whole function, 1 over x. We should know maybe that is a parent rational function. Okay, then you have the constant function g of x equals 1. And then finally x cubed. And what if you're not sure what that looks like, x cubed? Well, it doesn't really matter, because aren't you just making a table of values like we did up here? Okay, so create those tables over those specific intervals. And like I said, we'll go ahead and make a sketch of this in the notes. See if you can also tell me, where is this graph continuous? And where are the values for x that the graph is discontinuous? Last thing we have to do in the notes is you wouldn't be familiar with number 3 quite yet. Number 3 is a new function for us this year. It is called the greatest integer function. And what the greatest integer does is when you plug in values for x, I'll tell you the output, which is the y values. What's returned is the greatest integer less than or equal to x. Okay, that's how the greatest integers function is defined. So what happens is when you plug in integers, the output is that integer. But if I plug in a non-integer, what happens is it returns the greatest integer that is less than what you just substituted in. So for example, if I plug in 2, which is an integer, the output is 2. If I plug in 2.1, the output is 2. If I plug in 2.99, the output is still 2. Okay, so this is not a rounding function by any means, right? This wouldn't necessarily round up. It actually, in fact, always takes non-integers and rounds them down to the greatest integer less than what we subbed in. If I were to plug in 3, though, well, 3 is an integer, so the output would be 3. If I plug in something like 1/2, 1/2 is not an integer, right? 0.5, the greatest integer less than that is 0. Okay. -1 is an integer, so the output would be -1. But be careful with something like -1.5. -1.5, the output there would be -2. It's going to drop down to the greatest integer less than that. You know, same idea here for greatest integer of -1.9, also -2. So what on earth is this graph going to look like? I mean, we have kind of like essentially a table of values that I made here. It's not, I mean, we could plot some of those as points and see what happens. But let's think about this. So if I start at 0, 0, 0 is definitely a point on the graph. And anything I plug in between 0 and 1, the output will be 0. Okay, all those decimals and fractions between 0 and 1 are going to drop down to that integer less than what we plugged in. Until I get to x equals 1. When I get to x equals 1, the output should be 1. So you're going to put an open circle at the end of that little segment, and then jump up to y equals 1 and put a closed circle. And then similarly, anything between 1 and 2 is going to return an output of 1. But as soon as I plug in x equals 2, we've got to jump up to the next step. Put a closed circle at x equals 2, and you're going to see that pattern start to emerge where you get all these little segments that are closed at the left endpoint and then open on the right endpoint. And by the way, this would continue in this pattern for the negative side of the x-axis as well. Okay, it would go on forever and ever and ever in this direction. Okay, so I'll kind of stop there and put like a dot, 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 and a dot, dot, dot here. But yeah, it will continue on forever and ever and ever. So the domain of this function winds up being all real. So you can plug in whatever you want to the greatest integer function. But the range are only the set of integers, which mathematically looks like this funny looking z. Okay, so funny looking z, if you can squeeze it in there, means all integers only. Now, if you haven't guessed already, and I even mentioned it before, what does this graph actually look like? Looks like a series of steps. So very commonly, this graph is going to be referred to as the step function. Okay, and you can hop from one step to the next. So kind of a cool look, and there's definitely some real-life practical applications of the step function that maybe we'll talk about in class. But the only thing I need you to try before the next time I see you would be this sketch for g of x. All right? If you have any questions, let me know. Otherwise, we'll see you next time.